Welcome you all for the next part of mass transfer operations distillation. Uh, in the previous video we have seen simple distillation, fractional distillation and steam distillation. This video will be seeing checking out for tray distillation and packet column distillation. So let's look at the tray column distillation. So this is an industrial type setup. So it is most widely used for type of the distillation, quite commonly used in an industrial scale. It's a multi-stage process. Here is the equipment schematic sketch. The feed enters the column. It's a cylindrical column, big column, the way you have seen earlier, the tower. The feed enters somewhere in the middle. It has got distillation plates. Over the distillation plates, the feed moves in zigzag motion. Then it reaches the bottom of the unit. Then there it is heated up. It's called as bottoms liquid. It is heated up using the steam or a heating coil. For large scale operation, it is the steam that is used, and for a small scale, a heating coil may be used. Some portion of that, a fraction of that, is collected out as bottoms product. The vapor is reissued into the tower. It flows through the distillation plate. How it works, we'll see it later. Then it reaches the top. Through in this particular path, it comes in contact with the liquid. It becomes vapor and liquid equilibrium. Each plate there will be one equilibrium stage. That is why it is a multi-stage process. Multiple stages are present through the entire column. On the top, its vapor is collected and it is condensed. Some portion of it is sent back to the distillation unit. It's called as reflux, and a fraction of it is collected as overhead product. Now the ratio between how much it is uh, taken into the sent into the distillation unit and taken out as the product L by D is called as reflux. The ratio is called as reflux ratio. Alright, it looks something similar to fractional distillation. Here I have a question for you. It looks similar to the fractional distillation. Could it be possible that tray column distillation improves distillation purity? Just think over it and come back. You can pause the video. Yes, welcome back. You might have thought that there are multiple stages here, and multiple number of stages improves the distillation purity. Yes, you are right. Distillation column, tray column distillation improves the purity of the um, top product. So here we have a simulated video. Here is the column tower in which plates are there. You can see that there are troughs, the trays are there. This is called as a weir. The feed is entering from the bottom here, and that the feed is heated at the bottom. It is sent through the top. It is heated here using the heating coil. The liquid is pumped over here. It is pumped, it is moving, and it is fed here. The feed is entered from the middle. Now it overflows a channel. This is called as a weir. This is called as a weir setting. You can see that once it reaches the top of the weir, then it overflows. So here also you have another weir. You can ensure that some amount of liquid is always held up in the weir. So the extra liquid, it flows downwards. The liquid flows downwards likewise. It's in the zigzag motion, and it reaches the bottom of the tower, and it's called as bottoms liquid. Again it is heated up. The once that liquid reaches here down, that's again heated up. While coming down, it loses its heat and becomes slightly cold compared to the original input over here. Now the vapor that is issued here, once again it is getting heated, vapors are issued. It passes through this distillation plates. There are different types of plates, we'll see it later. Passes through that. At each particular such plate, it comes in contact with the liquid, and it reaches the top of the tower. It gets condensed. There are different types of the condenser. It is inbuilt condenser, a small unit. Otherwise there will be an extra additional condenser unit, and it will be sending the reflux. Now here it is overflowing. Some portion can be taken as the top product, and some other proportion can be sent as the reflux. Now that the reflux liquid, it flows downwards. It flows downwards over the wear over here. So when it comes down, it comes in contact with the vapor. There will be a liquid equilibrium. Yeah. So we have three different types of the plates. They are sieve plate, bubble cap, and wall tray. Three different types. We'll see the three different types and their advantage, how they work in principle. First one, sieve tray. Sieve tray, it is exactly like a sieve mesh. This is the physical version of how it looks like. You can see that there are perforations. One side it is completely closed, and one side it is open. That is nearly 25% of it is open. Remaining 75% is closed. This is the wear. This portion is the wear which holds up the liquid. So each tray has two conduits, one on each side, called as downcomer. So the liquid enters here and it flows downwards. The arrangement and how many numbers you require, the size of this hole, all are the design parameters. So what is a wear? Have you heard about this earlier? Just think about it, recall. All right. Where, yes, you might have thought about it. You would have come across this in the fluid mechanics, wears and notches. Normally this in the dam for hydraulic collection, that is water collection units, you'll be using it's present in the dam. So similar to that, water is held up over here, just like a dam. You have a reservoir, you have the liquid gets held up over here in this particular position. So I think we have a video here. This is the way it is flowing, and we'll see how this animated video shows how it works. So the vapor which is coming up through that perforation, it moves upward through the liquid. The liquid won't be able to come down, something like this. The liquid will be moving like this, zigzag. Vapor will be moving through the liquid, through the pores. So it will be moving upward direction. So here it comes in contact with the liquid. Alright, the second type, bubble cap trays. So this is a bubble cap tray. You have the cap over here. You have a fixed mechanism. Here a bubble cap tray, it has a riser or a chimney. This is called as a riser or a chimney, this particular portion. This is the cut section. The external section view looks like this. You have perforations over here through which through this cap the liquid vapor can come out, but liquid cannot flow inside. So how does it look like? Let's look at animated video. So this is the bubble cap tray. The vapor enters through the central cylinder portion and comes out. Right. Wall tray. So wall trays are something like this. You have a wall. Through the vapor will rise through that wall. It pushes the wall up. Performance are compared based on the liftable cap, how much pressures are present, vapor pressure is present, and based on that whether it can lift it up. So I have a question for you. What is the major difference between two types here, wall tray and bubble cap? Looked similar, both looked similar in design. What is the major difference between that? Try to think about it. Alright, the question is, wall rises with the vapor whereas bubble cap doesn't. True or false? Wall rises with the vapor whereas bubble cap doesn't. Yes, true. Bubble cap doesn't rise upward, it is fixed. Whereas wall, based on the vapor pressure, the pressure on that, it rises up. If there is no pressure like this, if there is no pressure, it closes. So let us have a look at a video here, video demonstration, how it works. So the liquid flows like this. It's a slow motion video. Liquid flows like this through that. Vapor flows here, and you can see that the wall slightly opens up and it pushes the liquid upward. So in this case, this has got a mixing pattern better than the sieve plates. That's the advantage of it. Vapor flow lift the cap. So caps move, wall caps move. Alright. Let's look at the next type, packed bed distillation. it is almost similar to the tray column distillation. The difference is in tray column sieve plate distillation tray column distillation, you have the trays. Here you have the packing materials. So vapor and liquid comes in contact inside the packed column. Here packed column, they are continuous and it's not stage wise. You don't have a stage wise, it is continuous operation. Even in the tray column or packed column, the stages above the feed, here it is feed, in this case is here, usually feed can be in the center also. uh, the number of stages above the feed, it is called as enrichment section or rectification section. The number of stages below the feed towards the bottom liquid, this particular portion is known as uh, uh, stripping section. So the stripping section will be at the bottom, enrichment section and or purification section, enrichment or rectification section you call, it is at the top of the column. So you have the packing materials and they are supported here, and through this the liquid flows downward, vapors are coming upward, exactly similar to the tray tower or tower distillation column, where you have the reboiler, it will be sending the liquid over here, and you reflux, even that is present, you can send the reflux. So vapor moves countercurrently upwards the column, liquid moves downwards in the countercurrent direction. So I have an animated video over here, let's have a look at it. So it's a steam distilled, the reboiler over here, it is heating, this is the liquid portion, the steam heats the liquid over here. Okay, this is the reboiler, the liquid which comes here, it gets heated because of the steam, so it is not shown here. The hot liquid, in fact it's a vapor, so that moves up the column. Please note that this is the advertisement video where they have shown the feed enters over here through the redistributor. This is called as redistributor. So this video they show all types of the distillation. This is called as random packing. The packing materials are randomly packed, and there are different types of the plates. This is the bubble cap, wall and sieve plate also. They are showing the sieve plate. Yes, sieve plate. So three different types they have shown. This is how it works. This is the plated column, random packing, and this is structured packing, which we'll see it in the next slide. This is called a structured packing. So different types of packing materials are present. Yeah, so we'll see that random packing. There are two types of packing. One is random packing, another structured packing. In random packing, this is how it was. This is why it is called random packing. The packing materials, any of this, they are packed into the column randomly. They are just dumped. It's also called as dumped packing. Materials could be metallic, non-metallic, or any ceramic. The first generation involves like this cylindrical, called as Raschig rings. They are called as Raschig rings. The second generation involves some more complex version, a pal ring. Pal ring becomes the second version, and see how it is slightly different from the Raschig ring. You have one more third type. They are still different in design. Second generation saddle here over here. This is also slightly different. Third generation is interlux metals. So the designs are still different from that. So you have the different types of materials available for the random packing. Raschig ring, pal ring, burl saddle, interlux saddles, or tellurite, tripacks. Different types are available. Now the advantage of this one is they withstand high pressure and they are cheaper. They are in cheaper design. You can withstand high pressures of operations. Now the question is this, you can think about it, why different types of packing materials are necessary. What is the speciality of Raschig rings in particular? You can pause the video, think about it and come back. Alright, the question is why different types are needed. Different types, they are based on the application. You can see that the surface area increases from the first generation to the second generation, then to the third generation. How the liquid and vapor come in contact with each other, mass transfer zones, that is also an important issue. How the packing density can be improved, that is also an important issue. So all these questions can be solved at different levels using different types of the material. Second one, corrosiveness of the liquid. If the liquid is corrosive, you require different designs. Now coming to the next question, what is the speciality of Raschig rings? If you see the Raschig ring, it is a cylindrical in shape, hollow cylinder. Now the important feature of this, characteristic of this is outer diameter is equal to the length or the height of the cylinder. L, length is L, diameter is D, L by D is equal to 1 for the Raschig ring. That is the speciality of Raschig rings. Let's look at the second type, structured packing. Structured packing, usually metallic or non-metallic or even ceramics are available. They are having a particular structure. You can see how it is structured. This entire thing is put into the column. So it has got corrugations, something like this. The liquid will move in one particular channel. Once it starts moving in, it will move, and the vapor also move in that particular channel. So there are different types of the channels: standard, flexi pack, Mellapack, Monts pack. All these are commercial names. So the first generation in 1940s, it was generated Panapack, first one. Then Sulzer came up with the second generation types. So the designs are slightly different here. Then Sulzer came up with the Mellapack. Then third generation and the present one, high capacity, high density they are called as. So it provides long uninterrupted channels for liquid and vapor flow. But remember, it's costlier than random packing. Structured packing is costlier. It produces lesser HETP than random packing. What is this HETP? Height equivalent to theoretical plate. Means with a low height, lesser height, it produces large number of equilibrium stages. Remember, more the number of equilibrium stages, more pure is the product. The vapor or the distillate that you collect, it is more pure when you have large number of equilibrium stages. With a small height, you can attain very large number of equilibrium stages. Now that is the concept of HETP. That is HETP, height equivalent to theoretical plate. If HETP is small, for a given height, same height of the packing, random packing or structured packing, if you can't take it, it will have large number of equilibrium stages. Random packing may have lesser number of equilibrium stages, so you can expect more pure product with the structured packing for the same height. So that's the difference between the two. All right, let's look at the summary. We have seen tray column distillation. We have seen that it is one of the commonly used distillation column with multi-stage process, industrial process. Here you have the different types of the distillation plate. We have seen three different types: sieve plate, bubble cap, wall tray. In this bubble cap, it doesn't get displaced, whereas wall tray, the wall get displaced. In the sieve, you have the perforation through which the liquid moves up. You have the weirs over here, which will help in the liquid hold up. The liquid is fed from the center, it will overflow the weir and it will come downwards. The liquid is heated up, it moves upward, the vapor moves upward when it comes in contact with the liquid at each stage. At each stage the equilibrium is attained. Now the the vapor moves upward, and it's condensed over there. Some amount of it is sent back. Upper portion is called as rectification section or enrichment section. The lower portion below the feed, it is called a stripping section. In the packed bed distillation, we have seen that packing materials are used. Here the mechanism is almost similar to the tray tower. The difference is the packing material. Two different types are there. That is, you have the random packing, three generations we have seen, and structured packing. Yes, that's the end of the video. Thank you.